I shall show that a parabola is a conic section. To do this, I must first define what a parabola is. Consider a straight line and a point some distance away. A parabola looks like this. And the precise definition is that a parabola is a curve such that any point on the curve must have the same distance from the fixed point and from this straight line. So that's how it's defined. Now this looks less familiar than the y equals to x squared curve that we would learn when we plot graphs. We know that y equals to x squared is called a parabola, but this is really the actual definition of a parabola. Later on we shall show that how this leads on to a y equals to x squared curve. Now let me define some names. This point here is called a focus, and that line is called a directrix. But then again, of course, today we would just think of this as one of a few possible definitions of a parabola. So using this definition, I shall try and prove that a parabola is a conic section. Now a conic section refers to the curve that is formed by a plane cutting through a cone. Okay. Now I'm going to have to try and draw a cone Let me draw it here. That's a right circular cone. Now, but to form a parabola, we cannot just cut this cone with any plane. If we cut the cone with a plane at this angle, then that would form a closed loop, which is an ellipse. If we draw or cut the cone with a plane that goes vertically, that would actually lead to another kind of curve called a hyperbola, which I shall not go into. Now, to get a curve that can be shown to be a parabola, I need to cut it with a plane that is parallel to a side of the cone. So the plane has to go this way. Now you can see that if the plane goes this way, if it goes parallel to this side, then the plane can go on forever, alright, without coming out of the cone again, or the part that goes into the cone will not come out of the cone again, because it follows parallel to this side. So therefore, I would have a conic curve. Alright, the section that is cut would just extend forever, which is what a parabola would look like. So, let me try and draw this. Let's say I have a plane. Okay, and this plane cuts the cone, say at around here, and it leads to some kind of a curved section. Okay, so suppose that this is the part where this plane cuts the cone. Okay, this part is a bit misleading. This part, I should have drawn it lighter. It should be below this plane. Now, next, we need to insert a sphere into the cone. Now we like this sphere to be touching the inside of the cone and just big enough to touch this plane that cuts this section. So it might say touch the curve at this point. There's a sphere touching the cone around here, and then it carries on and touch the section at this point, like that. Okay. So let's say that's the point where it touches this plane, and let me call that F. Right, you might guess that this is the point where I hope to show that it is the focus. Now, where this sphere touches the inside of the cone is a circle. Right, so the sphere is in contact with the cone along a circle. So now let me consider a plane that goes the plane that contains this circle. So let's say the plane looks like this. It goes up through here. It's a bit tricky to draw. Let's say let's say the plane containing the circle intersects this slanted plane along this dashed line. Okay, so one plane goes through this circle, one plane goes through that section. And you might guess that this line, which I shall call the line D, is what I hope to show to be the directrix. If that is the case, it means that I want to show that if I have a certain point on this curve, say point P, I want to show that the distance from P to F, to the focus F, is the same as the distance from P to the directrix, right? Which was how I defined a parabola. Focus to point, same distance as point to directrix. So the way to do that is to start by drawing this line, PF. Okay. Next, I would draw a line from the tip of the cone to P. Now notice that this line from P to F touches the sphere at F simply because the plane of this conic section touches the sphere. So a line on that, so since PF is a line on that plane, it would also touch the sphere. So PF is a tangent to the sphere. If you look at this line from okay, let me call this point A. So from A to P, this line AP also touches the sphere, right? Simply because AP lies on the side of the cone and the sphere touches the cone along this circle. So AP is also a tangent to the sphere. And since both AP and PF are tangents to the sphere, and the two lines cross at P, so therefore PF and AP must be equal. Right, so they are equal because they are both tangents to the same sphere. So those two lines are equal. Now what I really want to show is that PF is equal to the distance from P to point to this line D. Let me draw this line, the perpendicular line. Now since PF and PA are equal, I can also try and show that, let me call this point B, that PB is equal to PA. Now they really don't look equal. PA looks a lot shorter than PB, but remember this is supposed to be 3D. Okay, so it can be, the looks can be misleading. Okay, because both PA and PB are slanted. Right? PA is not really vertical as it seems. PA is along the sides of this cone. Okay. What I need to do now is I need a clearer view of this part. So let me try and magnify on that part. I need to redraw this bit. That's the cone again. Okay. Now I have this circle on the side of the cone. I have this point A. Let me draw it out here. A little bit more to the side. So I have the line going from A to, that's my conic curve. This is the point P, somewhere there. My line joining the corner of the cone to P. This line. Okay. And now I need this line D. And the line D lies on the same plane as, okay, see that the line D lies on the same plane as the horizontal plane going through the circle containing A, and this slanted plane that cuts out the conic section. So D is the line of intersection, so it lies on both planes. Alright. So D goes somewhere along here. Have a line D. Now my perpendicular from P to B, perpendicular from P to the line D would be this one, this length. call that B. Okay, so I have a plane that is horizontal containing the circle A, and another plane that goes this way containing the conic section. Alright. So, I wanted to show that PA is equal to PB, because if PA is equal to PB, then PB is equal to PF, which would then prove that this is indeed a parabola. So let's look at PA and PB and think about why they might be equal. You see, PA is along a slanted, is along a line from the corner of the cone along the surface of the cone. PB is actually parallel to one of this line along the cone. Alright, a line on the other side of the cone. So what this means is that both PA and PB, they are slanted to the vertical by the same angle. Alright, since both PB is parallel to one side of the cone, PA is along another side of the cone. So therefore, since they are both slanted to the vertical by the same angle, okay? And what is more, both A and B lie on the same plane. So that should be enough clue to tell us that PA and PB are indeed equal. Now to make that quite clear, let me draw the vertical from P down to this plane that contains the circle. So that's the vertical. Let's say it crosses the plane here at a certain point there, and let me now join this point to B on one side and to A on the other side. So in general, this line might not be a straight line. Okay, so but I do have two triangles now with this vertical line, and because, as I said, PA and PB are slanted to the vertical by the same angle, so those two angles are the same. Right? And these two lines are horizontal. So what we have now are two right-angled triangles with one common side and with two angles equal. So that tells us that PA must be equal to PB. They are both hypotenuse of the triangles. So we have PA is equal to PB alright, because they are hypotenuse of two congruent triangles. So let's see what we have done now. So previously I've shown that AP is equal to PT. Now I've shown that PA is equal to PB. So therefore, well, that's PA, that's AP, they're the same. Therefore, PT is equal to PB. Okay, let's remind ourselves what these are. What is PT? I don't actually have a T here, so yes, I must have. It must have been the F. That must have been PF. Alright, I've missed out that horizontal stroke and F became a T. So that's actually PF. So this is PF. PF equals to PB. So F is this point there, where the sphere touches the plane of the conic section. So now I have this property where FP, the distance of P of any point on the conic curve from this particular fixed point F, alright, is always equal to the distance of that point P from this fixed line D. And therefore this agrees with the definition of a parabola, that it is a curve where any point on the curve is always has the same distance from a fixed point and a fixed line. So this completes the proof. Alright. This means that therefore this conic section is a parabola. But not all conic sections are parabola, but this particular one, where the plane cuts at an angle such that the plane is parallel to one side of the cone, right? This particular conic section is a parabola. So therefore, conversely, we can say that a parabola is a conic section. Okay, we'll stop here.